Hello and welcome to our session, GitOps Compliant, How CommBank Multiplied Amazon EKS Clusters. My name is Michael Hausenblas. I'm an open source developer advocate in the container service team. And with me, we have Dario, lead engineer of the Commonwealth Bank of Australia. We will, in this session, have a look at how CommBank deployed Amazon EKS using the CDK and how they ran multiple Kubernetes clusters across multiple AWS accounts with multiple tenants, and how the regulatory compliance was enforced, and last but not least, how OPA Gatekeeper project was used to make sure the compliance is in place. But before we get started, let's step back a bit and make sure that we are all on the same page concerning GitOps. So what is GitOps? GitOps is kind of like your cloud-native operation model. So we're using Git as the single source of truth for the entire system state. All intended operations are captured in Git, are verified, and you have these two loops. On the one hand, the continuous integration, usually done by developers, and on the other hand, the deployment part. And you have a standardized workflow for everything end to end. And with Git, you have the place where all your cluster state, application state is captured and approved, and it's observable and auditable, which is super important for these regulated environments. All right, and with that, I hand over to Dario.
Hello everyone, my name is Dario Nascimento. I'm a lead engineer at Commonwealth Bank of Australia, where I lead a team that manages the container platform. One of the main challenges in large organizations is how to scale software development in an innovative, sustainable, reliable, and secure manner. To enable that, we built a container platform that aims to promote, implement, and enforce solid software and site reliability engineering principles across the entire organization. We standardized and developed strong opinions about most of the application lifecycle. Instead of repeating ourselves, we agreed on processes so that everyone can contribute to improve and automate the application lifecycle, providing a better experience not only for developers but for all the stakeholders involved. One of the core principles is that all applications must be declared in code, in Git, defining the state we want the system to be rather than the operations we want it to execute. And then GitOps operators, such as Kubernetes and CloudFormation systems, will ensure the service reflects the state you define it in code. That means humans only need read-only access for observability purposes. Any mutation is actually done by the GitOps operator, and it will synchronize the system configuration with the one we just defined in Git. So we kind of use GitOps and infrastructure as code as a mutability firewall that Mike was mentioning before. We built a container platform on top of Kubernetes and AWS, composing tools to, for instance, provide monitoring and credential management out of the box for all the users. And that's done by deploying Kubernetes add-ons such as AWS Secret Manager Controller, Kubernetes External DNS Controller, or OPA Gatekeeper. We use Kubernetes GitOps operators such as Argo CD and Flex to manage its components. Because GitOps is the way we interact with Kubernetes and AWS, we can improve and automate the IT governance processes involved in it, like risk, change, incident management. We can also provide a better developer experience, creating application patterns using tools such as Helm or AWS CDK. We aim to provide an outstanding developer experience so that the organization can deliver sustained and reliable innovation. Kubernetes and AWS are platforms that allow composing services to build a more opinionated platform, one specific to a company or to an industry. In large organizations, each team will have to naturally compose a slightly different platform on top of Kubernetes. But when managing systems, you must balance heterogeneity and scale. You cannot have both. You can manage a large fleet of similar systems, or you can manage a few very customized systems. In the end, most of the platform processes, like managing Kubernetes clusters, is also undifferentiated heavy lift. And this is especially important in regulated industries. Financial institutions run on regulated environments and must perform risk management to be compliant with the expectations of security and regulators. I consider them like bar raisers for processes and mechanisms. For those unfamiliar with risk management is a constant process that assesses what risks exist and defines controls to mitigate those risks. Controls are like requirements defined by security, by risk, by engineering teams, usually based on non-compliant standards such as ISO, PCI, or industry regulations. These requirements aim to detect, prevent, and remediate something that might happen. For instance, in security, to prevent unauthorized data access, we must ensure that all systems have authentication and authorization in place. Auditors will demand evidence proving that these controls have been implemented to ensure that the system is actually compliant. If each team would compose their own Kubernetes platform, each team will also have to repeat this auditing process and provide evidence that their version of the platform is also secure and compliant. And this approach will definitely not scale. So we built a trusted container platform, or a container as a service platform. We perform an extensive risk assessment to ensure that the platform is secure and reliable. And just like with the AWS shared responsibility model, we implemented controls on behalf of the users to reduce the length of the auditing process. The more opinionated the platform is, and the more controls are implemented by default, the better. Users only will need to implement the fewer controls when they have to create a new service. And auditors will also have a more extensive trust base so that auditing process can be much quicker. The platform itself can ensure many controls and requirements, for instance, backup, logging, data encryption. The platform team also automated compliance checks, running tools such as EKS Bench to demonstrate auditors that the platform and the applications running on it are actually configured correctly. We use GitOps to ensure that this secure configuration is applied to all environments correctly. Consider Kubernetes RBAC configuration. We define Kubernetes roles and role bindings in Git, and then the GitOps operator will apply these configurations to all clusters. Auditors can verify the configuration in a declarative code and be sure that this configuration will be the one running in all clusters. In addition to that, the Git commits themselves compose a ledger that auditors can audit and ensure what happened in the past. Some controls are still implemented by the users. Most of the controls are actually configuration best practices. For instance, users must have libness checks in their containers. Later in this presentation, I will explain how to use Gatekeeper not only to inspect user requests to Kubernetes, preventing them from breaking policies, but also to check the status of the applications running to ensure that they remain compliant with these policies. This allows us to create and manage multiple clusters, but that leads to the question, should we run one cluster or should we run multiple clusters? Should we have a single tenant per cluster or have multiple tenants? Should we run all the clusters in the same account or have multiple accounts? Service continuity and reliability is a must in financial industry. So when we designed this container platform, we optimized for service security and resiliency. In other words, for minimizing the access permissions and the blast radius. We converge on running one cluster per AWS account and 2 accounts per system, a non-prod account and a production account. A system itself is composed by multiple services within a single business unit. All applications in Kubernetes namespaces share quotas, secrets, access controls, service accounts, and IAM roles. So I tend to explain that namespaces are more of a group of resources that we can define access controls upon rather than actual isolation mechanism per se. And with that in mind, we took the following decisions: that a namespace will only contain one service at a specific release stage, an API in non-production, for instance. Each of the CI/CD pipelines will have their own IAM role, and that IAM role is constrained to one and more namespaces in a single cluster, granting minimum privilege even to automated release systems. Users can assume a read-only role to manage a specific service, and that will simplify a lot the RBAC in Kubernetes and the IAM policies. And users can only assume a write role using a temporary credential or a privileged access. And I recommend to watch one of the videos in re:Invent about temporary IAM credentials. Users also need to use AWS services such as RDS or SageMaker. Although IAM and AWS tag policies allow defining attribute-based access controls, it becomes very complex quickly at scale, and it's very hard to audit as well. So each cluster runs its own account, yet each account needs to be large enough to avoid multiple cross-account IAM roles, which are very hard to audit and manage as well. And this is a pretty common pattern as more and more organizations are adopting a multi-account strategy to segregate systems. So for those reasons, we run multiple clusters. We consider each cluster as part of a cell. A cell is an isolated system that does not impact other systems if it fails. That means if it has a well-defined bus radius and can be replicated easily. The container platform cell is a set of CloudFormation stacks that define the EKS control plane, the node groups, the Fargate, security groups, IAM roles. It also has a VPC private endpoint, so that all the API calls are kept within the private network. A code build project, which will be very important in this presentation, that will self-upgrade this cell, and also the GitOps operator Argo CD, which deploys and manages the policies and add-ons in the Kubernetes cluster. And this is kind of a set of CloudFormation stacks that is defined using AWS CDK or Code Development Kit. AWS Code Development Kit or CDK allows us to define and manage CloudFormation stacks using a programming language, in our case, TypeScript. In summary, developers use a programming language to codify their AWS resources, and CDK compiles and transpiles that code into CloudFormation. With CDK, we can code logic to assert the template parameters, ensuring that the configuration is correct. TypeScript modules and classes are actually type-safe, can be extended and composed to create complex AWS resource patterns, for instance, Lambda or API gateways. These patterns are testable and reusable because developers can publish their CloudFormation templates as NPM modules, and organizations can even build libraries of patterns for themselves. Check out the project AWS CDK Kits, which allows you to define Kubernetes deployments using a programming language via CDK. Overall, CDK is one of the best ways of defining your infrastructure as code when using GitOps. I recommend you to read more about it in the future. All clusters are defined in the same Git repo. We use a monorepo pattern instead of having a repo per cluster, and that allows us to build automation that tests the configuration of all the clusters and all the components. And that will help to prevent many human errors, but also to facilitate the peer reviewing. It allows us to build a single deployment pipeline that releases and upgrades to all the clusters in a single commit, saving a lot of manual work. Traditionally, a CI/CD pipeline will push the configuration, creating resources through a privilege role. Here, instead, we use a pull pattern, where the code build deployed in each of the clusters pulls the configuration and applies it only to the local cluster. That means the code build only has permissions to read from Git, pull the latest state, and update the local cluster CloudFormation. Code build here is acting as a GitOps operator, synchronizing one cluster with the configuration we just defined in the Git repo. We then can use code pipeline to manage the cluster fleet updates. First, it runs integration and compliance tests in a CI environment. After approval, the change is released. We upgrade the cluster fleet in stages, also called release rings. In each release ring, we start the code build process in several clusters in parallel. After each upgrade, we run the integration tests. If the test succeeds, then the code pipeline upgrades the next release ring, assuming more and more risk, because any issues will have a bigger impact in the organization. Code pipeline runs from a management account, assumes a role in the cluster account only to start the code build and to check its status. It's actually code build that has all the permissions needed to modify only that local account. In this way, if the management account is compromised, all clusters are still safe. There is no honeypot account. If the pipeline is triggered, all it can do is to trigger the code build synchronization. Again, that synchronization pulls the configuration from Git and synchronizes it locally. It does not have any impact. We can do even better. We can run code build periodically to ensure that this configuration is updated in every cluster periodically, so that the configuration is always synchronized with Git, and we can even remove the release process in rings that I just mentioned. These are kind of the flexibility that GitOps gives to cluster operators. We only use this process for clusters AWS resources, everything that's running outside of Kubernetes. Because inside of Kubernetes, there are already GitOps operators, such as Argo CD and Flux. As I mentioned in the cluster cell pattern, every cluster has its own Argo CD operator. Argo pulls the configuration from a centralized Git repo and replies that configuration locally. Argo CD is constantly synchronizing the cluster configuration with the one developers defined in Git. When the configuration is updated, Kubernetes runs its reconciliation loop to update the cluster state. If a resource is not defined in Git anymore, Argo and Kubernetes will remove it. If any resource was modified manually, Argo and Kubernetes will restore the correct state. Whenever the configuration does not match Git, Argo reapplies that configuration automatically and sends an alert to our monitoring system so that we can investigate what happened. For instance, we create an Argo CD application that pulls RBAC configuration for a cluster. If a developer somehow gets privilege to change that RBAC policy, Argo CD will quickly override that. Zooming out, Argo is running in each of the clusters, pulling the configuration from GitHub using a read-only credential. And that's a better approach than using a CI/CD to push configuration. All credentials are local to the cluster, no privilege or shared admin credentials are required. Argo CD has a security policy that allows us to define what actions are allowed in each of the components. For instance, we can constrain a Git repo to modify only a single namespace. In GitOps security model, we can add a new cluster easily. We do not need to modify the existing pipelines. The Argo CD in the new cluster will pull the configuration and apply it locally. We use conditions in the template to have different patterns and parameters for different parts of the cluster fleet. For instance, policies configured in production versus non-production. All the cluster's components are defined as code, mostly Helm charts, in a repository that I mentioned before. Argo CD deploys the components in each of the cluster. This is a non-extensive list of all the integrations available, but here are some of the highlights. The AWS controller for Kubernetes, which allows to deploy AWS resources like S3 buckets using Kubernetes API. The secret manager controller, which gets secrets from AWS Secret Manager and injects them into the deployment. Some of these services expose Kubernetes via Kubernetes API using custom resource definition. So for instance, in Prometheus operator, we define custom resources that users can use to define what endpoints need to be monitored and also to set our thresholds. And that's a very powerful way of actually exposing services in your container platform. And that will definitely be a topic by itself. As for cluster configuration, we use Argo CD to distribute a template configuration for namespaces in RBAC. When Argo CD applies this RBAC, users lose privilege access, and we can enforce least privilege. In addition to that, Argo CD also creates storage classes, pod security policies, and gatekeeper policies. A cluster must ensure that its own data integrity remains compliant and consistent without having to use any external tools. Just like with an API with a database, the platform must ensure that the state of its clusters is consistent regarding of how it's being consumed. In databases and APIs, we have database constraint of integrity and logic in the API that ensure that data integrity happens. In Kubernetes, an approach to do so is to use Open Policy Gatekeeper. Open Policy Gatekeeper allows to define policies on Kubernetes resources, checking them before deployment and while running. Gatekeeper implements a Kubernetes admission webhook API, which Kubernetes invokes before accepting a resource change. Then, Gatekeeper can decline, accept, or mutate that resource. Just like in a common API, developers implement logic that may decline a request. In Gatekeeper, the logic is defined in a decorative programming language named Rego. Rego empowers developers to define policies to assert the content of a JSON document, which is ultimately what a Kubernetes deployment is. For instance, a policy can enforce that the Kubernetes deployment must have a liveness check or ensure it uses an authorized Docker image. Gatekeeper and admission webhooks empower operators to create robust authorization mechanisms. However, Open Policy Rego has a steep learning curve. Gatekeeper makes this easier by abstracting Open Policy Rego with policy templates. An example of a template in the demo will be to whitelist Docker registries. The templates aim to hide the Rego code so that the users can parameterize the template in an easy way with the Docker registry that they want to whitelist. However, there are not many extensive public policy template libraries yet. And moreover, sometimes it's a bit easier to code your own admission webhook. For instance, if you want to check that the Docker image was scanned. When Gatekeeper denies a request, the policy can return a message informing the users why it was declined and how they can fix it. The main objective here is to empower developers. We want to ensure that the best practice of system configuration are applied to all the applications running in these clusters. Using GitOps, we can also run these policies in Git webhooks and provide a feedback in the developer pull request. These are just like static code analysis policies that check if the Kubernetes deployment is correctly defined in the code. We can also check if any Kubernetes application running in the cluster is actually breaking any of these policies, which would mean that the cluster integrity has been compromised. Here are some of the policies. The main objective is not to block developers again. The goal is to empower them to follow the best practices so that the service is well configured and reliable. For instance, consider Kubernetes pod eruption budgets, which define how many replicas of an application need to be available during a cluster upgrade. If this is misconfigured, all of the application replicas will be terminated during a cluster upgrade and the application will have a downtime. Another example is to ensure that all the resources are well tagged, because this is critical for service management, but also for attribute-based access controls. So in this demo, we'll define how EKS cluster is defined in CDK. The first, we define a CloudFormation stack, and then we create the EKS cluster. To this, we'll add capacity with a node group of 3 T2 micro instances and also a Fargate profile. But last, the only thing we'll need to deploy on this base pipeline is actually the Kubernetes manifest to run Argo CD. This stack is then deployed using a code pipeline. So the first thing we do here is to pull the source code from Git. We compile this TypeScript CDK that generates a CloudFormation container in the cluster stack, and then it deploys the CloudFormation in this account in on-prod, runs a very simple test to make sure that the API is available, and then by last, it also deploys the same in this production account and runs exactly the same test. This is how it looks like in the AWS console. It pulls the source code from Git, it builds it, publishes the CloudFormation templates to S3, so we have like a code published in a static way, and then for each of the accounts, it's where it's going to run the code build to pull the code and pretty much synchronize in a kind of GitOps operator way. And this will have like multiple clusters with the same risk level being upgraded in parallel. And if everything is successful, then it does the same thing in production, and we'll have more and more levels of release. This is how it looks like when you have the Argo CD running. We have a root application in which you define all other applications, and in this way you can use Argo CD to add or remove applications. And this application here is actually Gatekeeper, which we deploy from its upstream Helm chart. Then we have other two applications. This one is a library of policy templates that we defined in Git. This particular policy will whitelist Docker registries that will be allowed to be used in this cluster. So we open the policy template right now, and here is where we define the open policy rule that implements this logic. We get all the containers from the deployment spec, and then for each of these containers, we'll verify if the Docker image of that container starts with one of the parameters that we have here named as repo. If the image does not match any of the allowed repos, then it shows an error message. For instance, error message container nginx has an invalid image repo, docker hub .nginx, and the allowed repositories are ECR. And this is also deployed by Argo CD. Then we need to parameterize this policy. So here is where we define the policy parameters, allowing only to use the ECR registry. So now we'll deploy this application. Here's like the ECR repo that we will allow. And now we'll deploy an application that will have a standard Docker image. So this application uses this Docker image, Jupyter notebooks, and we'll apply this configuration now. Okay, so the deployment was still successful. Let's describe the policy we just created. Here is kind of what we're expecting to happen. Like we have the alert and the error message we'll be expecting, saying that the allowed repo are DCR. The policy is being violated. And the reason why the deployment was so successful is because we're running on dry run mode. So we're not enforcing this policy. We're just verifying it's being checked or not. So we're going to change this policy from dry run to deny. So that means that we'll block the deployment. So we're updating now in Git. We're changing the policy. This is also managed by Argo. And we're just going to commit that policy now denying the deployment. So we're pushing. And now we open Git, Argo CD, and we'll expect Argo to synchronize. There we go, we are out of sync. We're going to synchronize, pulling the latest configuration. And now if we check the policy, we can see that the enforcement policy is now denied. So now we're going to try to deploy this application again. We have no issues because the running applications keep running, which is great. You don't want to break your systems in runtime. And now that we're trying to apply this again, we'll see that the deployment is actually blocked. And it explains why it was blocked so that the users can go and fix the problem that was raised by this policy. So the overall message is that if you want to scale your Kubernetes platform, you should create patterns and use GitOps to ensure that these patterns are correctly defined and deployed at scale. Thank you for watching, everyone.